On to question number 2. Now, question number 2 was all about low-level programs. And the question it asks, first of all, is, what is a low-level program? Now, this is a definition that you can learn, and you just have to know this. So, if I show you what a low-level program is, then you'll be able to see. So, we are used to programming languages like C++. Maybe you've done a bit of Python and various other languages. And all of these languages are high level. The point about it being high level is that the computer does not understand these languages. So the computer is confused by this. It has no idea what it says. And we also then have low level languages. So, low-level languages is the language of the computer. A low-level language, when it's actually stored on the computer, will be in binary. When we want to look at a low-level language as a human, we use a code called assembly. Now, assembly language is the language of the little man computer, as we can see here. And what we've got is, first of all, you have here the assembly instructions, so INP, STA, INP, sub. This is the line number here. And then over on this side, on the right hand side, that's the instruction set. So when this program is run by the little man computer, INP here, I just highlight that, will be translated into a number, and we can see here that INP is 901. So what that means is this will be translated, tablet going wrong there. This will be translated into 901. Next, we've got STA 99, store address in 99. And if I have a look in here, STA is 3XX. So that gets translated into 399 because it's store 99. Next, we've got an INP. We already know that one. 901. Sub. Let's get ourselves a different color here. Sub 99. We find subtract over here. We can see it's 2XX. So that is going to be 299. BRP 07. Again, we come down, we find it, and we can get these numbers. In the little man computer, these are represented in normal numbers in denary. But in a real computer, it will be represented in binary, like this. So, the thing is that in a low-level language, one assembly code or one line of binary refers to one single processor instruction. It will have two parts to it. So it will have an op code, also sometimes called the operator, and it will have the operand. So if the opcode is, let's say, 5, which is in the little man computer load, and the operand is 22, it means load address 22 into the accumulator. High-level programs are much more complex than low-level programs. They are easy to read by humans. So humans are happy with high-level programs. There are translators for high-level programs. There are a few different types. One is called a compiler. Compiler. And one is called an interpreter. We'll go over that knowledge elsewhere. So a high-level program is easy for people to read, but needs to be translated for the machine to read. A low-level program is in machine code. It's represented in binary, and it can be run directly on the processor. So we just need a couple of those points in our question here. What is a low-level program? It is a program where each instruction corresponds to one processor instruction, or it's a simple program that is run directly by the computer. It's a program consisting of processor instructions. So there's several possible answers. Mentioning binary will also get you an additional mark. If you say it's a program that high-level programs are translated into in order to run it on the processor, again 2 marks. The next question part 2, is quite simple. What we need to do is we need to use this program we've got up the top in order to fill out this table. So you have to do a few things. First of all, the program counter starts at 0. Knowing this gets you 1 mark. And we can see from up the top that the first instruction, INP, is 901. So that means into the instruction register goes 9, into the address register 01, 901, which is an input. And it says up here the user enters 4 and 5 into the program. So the input here is going to be 4. There is no output, and what the input statement does is it puts this into the accumulator. So that will be 4 as well. We have no idea what's in cell 99. Then the program counter increments. So we're going to do instruction number 1. So there's another mark forgetting that the program counter increments by 1 each time. So instruction number 1 is STA 99 or 399. So we write in here 399. There is no input because we're not doing an input statement. There is no output. And the accumulator remains at 4, and we store that as well in cell 99. We come up here. The next one is getting another input. So 2 on the program counter because it goes up by 1. Again, it's 901. And this time, as it says up the top, we're going to use 5. There's no output. The accumulator becomes 5 because that's what the input statement does. And RAM cell 99 remains at 4. So one thing changes at a time. Now the next instruction, sub 99 or 299, got from over here, means that instruction number 3 is 299, and what we're doing is no input, no output, but we're taking the contents of RAM cell 99 away from the accumulator. So that will be 4, and we take it away from the accumulator, so the accumulator is 1. Next one says branch if positive. So BRP, let's find it over here. So it's 8XX and 07. So instruction number 4, 807. No input, no output. Accumulator is 1, and RAM cell 99 is 4. And it says if the accumulator is 0 or positive, then we jump to instruction number 7. So we put a 7 in here. So the program counter is now 7. There's a mark for that. And so instead of going on to instruction number 5, we actually get instruction number 7, which is LDA 99. LDA 5x. So 599. No input, no output. And the RAM cell 99 is loaded into the accumulator 4, and that is left in there like that. Then it will go on to instruction number 8 because it's not a branch, and instruction number 9 is the same, which is sub 99. So 8, and then we're going to sub 99, which is 299. No input, no output. We take that off of that, 0 and 4 there. Then we've got instruction number 9 is a repeat of that, which is 299. Minus 4 in there and 4 in here. The last instruction, number 10, well, the last but one, is output. So output is, instruction number 10 is 902, it's in the table. And then we've got here an output of minus 4. Sorry, I've gone a step ahead. There we are. The output is minus 4 because it's what's in the accumulator. Minus 4 and 4. And the last instruction is 000, which means halt. So there were marks for, first of all, getting a 0 here, that the program counter was going up. There's a mark for doing the branch properly. There was a mark for getting the correct result, and there was a mark for decoding the instruction register and the address register properly. Last thing, we've seen from this that the purpose of the program counter is to keep track of which instruction needs to be run next. So we've got instruction numbers down the side here, 0001 all the way up, and the program counter tells us which one to run next, and hence the branch instruction manages to get us to jump. So the purpose of the program counter is determines the instruction to be fetched and run next. There we are. Good. We'll go on to question 3 in a moment.